help me welcome Mayank.
Thanks a lot for attending this session. My name is Mayank Mangla, and I'm an imaging architect at ADAS business unit of Texas Instruments. ADAS, as Matt touched upon, stands for Advanced Driver Assist Systems. These are basically electronic systems which make driving easier for a driver, whether a car or a truck or any other vehicle. It's about can use camera or non-cameras to make the driving easier. So we'll see some of the challenges which we face in ADAS imaging and how we use MIPI CSI2 to solve those challenges. So some of the applications, it ranges from very basic applications to some of the very advanced, high bandwidth demanding applications. All of you must have used a rear camera in your cars, which is becoming almost a standard feature in most cars. It's kind of mandatory in all US cars starting 2018. But it doesn't only stop at showing an image. There's a lot of intelligence you can add to the camera for back-over prevention and object detection kind of applications. And from there you can advance to, so that's basically one camera use case. You can advance that to a surround view. SV stands for surround view. What it means is a car which has cameras all around it, and a central processor acquires images from all the cameras, does the image processing on them, and stitches them to create a bird's eye view so that the user can see the natural view as if there is a camera on top, and he can see objects all around the car. And that makes it very easy to park into tight corners and avoid objects or avoid moving objects, pedestrians, or approaching cyclists. So that gives a whole different category of safety in driving, particularly in crowded cities like Bangalore. And there are a lot of other applications. Matt also touched upon CMS. CMS stands for camera mirror systems, also called mirror replacement. So this is an example of where a small camera, the A pillar of the car, replaces the optical mirror, and the camera is streaming raw images and sending them inside the car, and then the processor is processing them and rendering those images on the display. So basically your mirror, the optical mirror goes away and a small display comes inside, and what's left outside the car is only a small camera, which reduces the air drag by say up to 6%, which results into 1 to 2 miles per gallon saving and a huge carbon dioxide reduction saving. So a lot of other applications. One of them is, so this is a radar plus LiDAR. This is a non-imaging use case. And we'll also see how MIPI CSI2 is camera serial interface, so designed for cameras. But in this presentation, we'll also see how it is used for non-camera devices. So some of the challenges we see in automotive imaging, and when I say challenges, these are challenges which are unique to automotive, over and top of what we see in consumer imaging. So first, faster frame rates. Why faster frame rates? Because when a car is moving at 100 miles an hour, typically that's where the automakers try to calibrate it. Think of driving on Autobahn. If a car is driving at 100 miles an hour with a camera replacing an optical mirror and sending live images, then you need the frame rate to be very, very fast to avoid jitter. So that high frame rate basically increases your bit rate per second. Then sensor resolutions are going up, as Matt also mentioned. The current generation cameras are 1.3 megapixels, but they are now going to 2 megapixels, 4 megapixels, and 8 megapixels, and probably beyond that also. And then high dynamic range. Why high dynamic range results into high bandwidth is because the way dynamic range is enhanced is, what it means is a low dynamic range image can either look at either the bright pixels in the image or the dark pixels in the image. But you have very dark or very bright regions in the same scene, then your automotive, the CMOS sensor cannot handle it. And that's handled by taking multiple exposures. So for one image, you're going to take 3 images and then combine them based on each pixel's signal to noise ratio. And that requires all the 3 images from the sensor to be sent over to the processor. So your bandwidth requirements simply went up by 3x. So when you combine them all together, you see a very, very high bandwidth use case. Other challenges in automotive multi-camera systems. So for example, surround view, there are 4 cameras, all of them sending data to the processor. And the processor not only has to receive the image from the camera, it also has to distinguish which pixels belong to which camera so that it can adequately process them. It needs to to distinguish them, and at the same time it has to handle multimodal fusion. What I mean by multimodal is different modes of sensing, like camera imaging is one mode of sensing, radar is a different mode of sensing, and I'll go into a little more detail later. But the idea for multimodal fusion is all the modes of sensing have their own limitations, their strengths and their weaknesses. So for example, camera is very good at identifying objects, but it does not work very well across all kinds of weather conditions. Like in low light or rain or fog, it does not work very reliably, but radar works quite reliably there. However, radar is good for detection, but not for classification. So when you combine the two, you basically get a lot more accurate decision, and your safety or accuracy goes from 90% or suddenly to 99%. Think of the way your accident rate falls down from 10% to 1%. So that's great. The problem is now for the same algorithm, you are now acquiring two images, one from the camera, one from the radar. So your bandwidth goes up. Other constraints, package size and pin count. Now if you have 4 cameras plus radar, all sending data over a legacy, say 12-bit, which was a legacy interface, you're going to need about 40 to 50 pins. So that's a huge area cost. But on CSI, and I'll show that later, you can do the same job with up to by 6 pins or maximum 10 pins. So that's a huge reduction in pin count and in the area size. Signal integrity is a major factor, and CSI2 helps here because of using low voltage differential signaling. It can go up to much higher clocks, still maintain signal integrity. And the cable usage is always a constraint, so because of the channel length and signal integrity issues, by using a more robust protocol, we're able to use cheaper cables and reduce the overall bill of materials. And finally, when we talk automotive, we always talk about safety, we talk about quality. Why is that important? For a cell phone, the typical life is about 2 to 3 years. That's when people replace their phones, throw them away and get a new phone. But for a car, the life is easily up to 15 years or even beyond that. Then safety. Most consumer applications are not safety critical. If your phone crashes or a camera stops working, your life doesn't depend on that. But in a car, if a camera is telling the user when to apply brakes, then the drivers or other people's lives depend on that camera. So that's why there are very high quality and safety requirements for automotive imaging. So this is one of the example topologies. This example is for a surround view kind of a system. So you will see there are 4 cameras, and there is a vision processor which needs to get the image from these 4 cameras, process them, and render them on a display. In a consumer camera, you will see the camera. In a consumer system, you will see the cameras will be connected directly to the vision processor. But in automotive, typically the cameras are located very far away because a car is much bigger than a mobile phone. So that the channel length is going to be easily 10 feet, 20 feet. In cases of big trucks, they can even be 40 feet. And channel length is a limitation of the current CSI2 protocol. So right now, how it is handled is by using a serializer-deserializer pair. A serializer is a device which takes the CSI2 stream, converts into an analog stream, and sends it over a long analog cable. On the other side, we have a deserializer device. Deserializer does the exact opposite. So it takes an analog image and converts it to digital, extract the serializer packets from CSI2 stream, and sends it to the vision processor over another fresh CSI2 byte stream. So the advantage is, it solves the channel length problem. Second, the deserializer also acts as a 4-camera aggregator, and we'll talk in a little more detail how it uses some of the very specific MIPI defined features to do the aggregation job. And it uses something called virtual channels, which actually is not so much used in consumer imaging, and automotive is really making that the benefit of that feature given by MIPI protocol. So summarizing why MIPI CSI2 in automotive: A, low power. Compared to the traditional parallel interfaces, it can do the job at much lower power. High speed transfers. Because of differential signaling, the clock lane and data lane can be clocked at very, very high frequencies. That results into high speed transfers. Low pin count. As I said, so the very minimal CSI2 system, you need 2 pins for clock, 2 pins for data. So with a 4-pin interface, you can have a very high bandwidth, like up to 1.5 gigabits per second lane, but you can scale it up. And CSI2 allows up to 4 lanes. If you need 4 lanes, you need to add 6 more pins. So with 10 pins, you can have a 6 gigabits per second interface. Versus if you have to do it in parallel, and with 6 gigabits per second, you can easily connect up to 4 high resolution, high frame rate cameras. To do the same thing over parallel interface, you're going to need about, like, if it's 12-bit camera, 12 bits into 4, you're going to need 48 pins. And the same job you're doing in CSI2 with just 10 pins. Now, standardized protocol. This is important because there are some other serial protocols, like OnSemi has a HiSPI protocol, which has some of the similar properties as CSI2. Now, the disadvantage of HiSPI is it's proprietary of Aptina, which means that all the processor makers, all the receivers have to comply to that protocol. Versus CSI2 is industry standard, it is recognized by all the players in the industry, and everybody can now do, all they have to do is adhere to MIPI specification, and then they're guaranteed to be interoperable with other receivers and transmitters. The next big advantage of CSI2 is virtual channels, and this is something which allows multi-camera aggregation. So 4 cameras sending their pixel data on a single link, and the receiver can still receive them and distinguish them by virtual channels. Now, some error detection and recovery. So sync codes, start of transmission, end of transmission kind of codes. ECC code, which can detect 2-bit errors and correct up to 1-bit error. And a CRC checksum. What this checksum does is, its checksum is calculated packet by packet, and this is a part of MIPI protocol, so it's all done in hardware. So without any extra software processing or without any extra DSP or GPU processing, the transmitter can compute a checksum for each packet, and receiver can generate a checksum and compare with the checksum it received, and if there is a mismatch, it's going to flag an error. So that results into much more robust and sturdy transmission. And finally, safety. So there are a lot of extra features provided by CSI2 protocol which can be used to enhance the system safety. In automotive, the safety is categorized by a level called ASIL. So it goes from ASIL A, B, C to ASIL D. And a higher ASIL level requires more functions on the processor side to detect errors and to detect failure conditions. So for example, one of the examples is ancillary data. So camera is not only sending you pixel data, it can also send you some ancillary data like what was the operating temperature. And typically what we see is cameras start failing at high temperatures, and if the temperature information or any other ancillary information also comes to the processor's machine learning algorithm can use that in the training data set, and based on that it can decide if something is failing, is it expected or is it about to fail, and then it can alert the driver or take the vehicle into a safe state. So let's talk about how do multiple lanes are handled. And it's a kind of a clean solution which is proposed by or implemented by CSI2, and all the compliant receivers and transmitters are going to stick to that. So first, a simple example of a transmitter which is sending a byte stream in this order, in the serial order, and it goes over the link, and the receiver then receives it on the same order and keeps on flushing it out to external memory. So you see here byte 0 is already written out, byte 1 to 5 are in FIFO, and one by one they will be written out, and the new bytes will keep on coming from over the link, and that's a continuous ongoing process. So this is a single link system. Now within CSI itself, you can now scale it up from 1 lane to 4 lane, and it is kind of not visible to the application processor. So it will continue to receive the stream in the same way. It does not need to know whether at a transmission level 1 lane was used or 4 lane was used, as long as the receiver is correctly programmed. And the way it's done is, in the protocol defines a distribution logic and a merger logic. And again, because it is a standardized protocol, all your receiver has to do at the design stage is to comply to that algorithm, and then is guaranteed to interoperate with the transmitter. So transmitter is going to get this serialized bit stream, and the first byte goes to lane 1, second goes to lane 2, and so on. And after that, byte 4 goes to lane 1, and so on. At the receiver side, the merger algorithm does exact opposite of that. So while it is receiving byte 0 from 1, and then takes byte 1 from the second lane, and so on, and then it reconstructs the same byte stream, and the image signal processor or the GPU gets the stream as if there was no distribution merger had never happened. And by doing that you get 4 times the bandwidth without any extra software processing. Virtual channel. So what a virtual channel means is, on a single link, you can have 4 cameras, different pixels, different cameras. The cameras can be different resolution. They may not be even be cameras. They could be camera or radar or LiDAR combination. And they're all traveling together. So how does the receiver know which byte is a pixel and which byte is a radar data, or if byte is a pixel, which camera does it belong to? And the answer is virtual channel. So virtual channel is an ID defined in the CSI2 packet format. So CSI2 packet header has 2 bits for virtual channel and 3 bits for data types, which means there are 4 VCs and 8 data types allowed, which gives you up to 32, there's some reserved values, so about 25 or 26 different combinations, right? And this is an example where there are 4 cameras connected over a link, and they're all sending the data together. There is an aggregator in between who takes the 4 images, concatenates them into combines them into a single CSI2 stream, and then sends it over the link to the processor. When the processor receives, these are the byte stream. All the bytes look alike, except for the VC ID. So the camera, assuming this is camera 1, so or camera 0. So all the bytes from camera 0 will have the VC ID 00 in the packet. Similarly, camera 0, camera 1 will have ID 01. And the CSI2 receiver can understand that VC ID. It can parse it in hardware, everything in hardware, so no software processing. And in the hardware, it can have 4 DMA addresses. So each of the pixel data or the buffer, frame buffer, can be DMA'd to a different location in the memory. So by the time the ISP comes to process the data, it is already cleaned out, it's already segregated, and you have one clean buffer for every camera. So, I mean, and this could be camera or this could be radar. So when it comes to your image processing or your machine learning algorithms, they get clean data without any need for any further parsing. Similarly, there is a concept called data types. What data types mean is, for a camera, it's sending you pixel data, but it also sending you some kind of ancillary data. And if the data gets mixed up, then your image signal processor will reach to wrong results. So by using data types, each different data types comes with a different ID, and CSI2 protocol engine parses it in hardware, separates them out, and then you get one clean frame of pixel data and another clean buffer of embedded data or ancillary data. And then it's for your image signal processor or your GPU processor to decide how to process that. Okay. So this is an example of a surround view algorithm and high level implementation strategy. So in a surround view camera, there are going to be 4 cameras located around the car. So there's going to be front, back, left, and right camera. Typically, those cameras are very wide-angle cameras, almost up to fisheye, 180-degree field of view. The problem with those is the image you get is not linear. So these have to be passed through a lens distortion correction. And it's important that before the lens distortion correction receives these images, the images are already parsed out, separated, and this is what MIPI CSI2 does. So once you have the clean images, then lens distortion correction does the rectilinear transform followed by a perspective transform, and after that a GPU or another hardware accelerator combines the 4 images to create a bird's eye view looking like this. And once this is what the driver sees. The 4 images are, okay, it's not working. So you see the 4 images are just showing the very highly distorted fisheye view around the car, but after all this processing, the driver sees this. So it's basically it's able to see everything around itself, including the tight parking slots, the pedestrians or any cyclists driving by, and it can lead to much safer driving decision. So how it is done in one example is, it's done by using a deserializer hub, one of the TI family parts, the DS90UB96X, which allows the channel length to go up to 40 feet using FPD-link cables. Also does a 4-camera aggregation. So it receives 4 cameras over the coaxial cable, 4 inputs, converts them to digital domain, and creates a new CSI2 byte stream where the pixels from all the 4 cameras are aggregated with different virtual channel IDs. The receiver host processor, again from TI family, TDS stands for TI Driver Assistance SoCs, which has a compliant CSI2 receiver embedded inside the SoC. It receives the incoming stream, parses them, separates them out, and then does the final processing of lens distortion correction, image processing, and GPU. So this is just showing that surround view is, what I showed you was an inter-level surround view, but now there are more advanced surround views implementations where you can do park assist or self-parking, like a valet feature when you drop off the car and the car goes and parks itself. More obstacle detection features, or even a trailer hitch. So think about a trailer, a truck with a trailer attached to it. The problem with that is trailer is very far behind, and for the driver, it's not easy to see what's going on behind the trailer. So apart from the surround view cameras, you can add one more trailer hitch camera, again feeding data to the same processor. So even more bandwidth, more processing required. So in summary, surround view, the challenge is high data rates, up to 3 Gbps in current generation, and as the resolutions go up, they may go up to 6 Gbps. High pin count, so 4 cameras need at least 48 pins. CSI2 does that with anywhere from 4 pins to 10 pins. Long channel length, this is one of the limitations of current CSI2. I know the working committee is working on increasing the channel length, but right now, because cameras are located far away from the processor, we have to use SerDes chips for the analog. And sync. Sync is important because when you're stitching 4 cameras together, in automotive there is always motion, the car is always moving. So because of moving motion, if the cameras are out of sync, then you're basically combining 2 images which are have a time shift, and that's going to result to some kind of artifacts or distortions. So that's one more thing which UB960 devices do. It can help you force sync on all the 4 cameras, and this is also one of the current generation CSI2 limitations which the working committee is fixing on in the next generation. Next example, multimodal fusion. As I touched upon a few minutes back, multimodal fusion means a passive sensor like a camera and an active sensor like a radar, LiDAR, or ultrasound. There are different kind of modes depending on the application. For mid and long range, you need radar. For very short range, you can use LiDAR. And for very, very short, like very proximity range, you can use an ultrasonic sensor. If you have ever seen your car going beep, 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 beep when you back up and there's no obstruction right behind the car, current generation, it's all done by ultrasonics. So using a bunch of all these kind of modes of sensing, you can create a system which is cost optimized as well as very robust and can work across most of the weather and light conditions. The problem, lot of data to process and lot of data to acquire. So the challenge is, again, high data rates. If you take a very simple system with just 1 camera and 1 radar, you're looking at 3.4 gigabits per second. High pin count, again, the more number of devices need more pins. And imaging format variations. Now the format of a camera is going to be different from a radar output format, from an ultrasonic output format, from a LiDAR output format. And how CSI2 helps is, as we have already seen 4-lane interfaces, blah, blah, blah. So, but in terms of image format variations, CSI2 supports a lot of different kind of formats from 8-bit to 12-bit to RAW to YAV and custom formats. Because of that, devices like radar can easily extend to CSI2 protocol without making any design changes. Even at the serializer and deserializer chips, did not need a redefinition. So with the current technology, with the current MIPI protocol, the radar just basically implemented the same protocol which was designed for image sensors, and it works interoperably with SerDes chips and with vision chips. So this is one of the topologies for fusion. I will not go into details of the SLAM processing or the software processing. What it's showing is for a car like a Mercedes S-Class car or even the future Tesla, you're going to have a large number of cameras all around the car, can go up to 10x, a large number of radar devices, a few LiDARs, a huge bunch of ultrasonics. Ultrasonics are cheap, so the OEMs like to place them everywhere, and then some thermal or IR sensors. And all this image has, all this data has to be acquired, brought in over a low pin count, high bandwidth, low power interface. And then it goes into perception processing, where it goes into fusion algorithm, which can take further inputs from an IMU, inertial motor unit, or GPS or a navigation software. And finally, it creates a view. It could be an augmented reality view, or it could be something which user does not see the car, only alerts the driver when there is a problem. So important thing, for example, GPS will give you the coordinates of where the car is. The maps will give you an indication of if you're driving through downtown and there is a stop sign or there is a red light, then it's going to give you an indication of you're somewhere around a stop sign, so you need to stop. And then the camera is going to give a confirmation of that. If the camera can see a stop sign and classify it as a stop sign, so by having all this information, the car can reach a decision that the driver needs to apply the brakes. In case there is no driver for a self-driving car, then not having this information can lead to a traffic ticket, or it can lead to an accident, or can lead to a death. That's why more and more information added on can increase the reliability of your system. That's what there are different levels from level 1 to level 5. Level 5 is fully autonomous when there is no driver, there is no driver control, and the car is 100% efficient of driving, not only in highway, but also in city, in downtown, in very, very tight spots. That's where more data and more bandwidth helps. And to acquire more data, you need a high-speed interface like CSI do. So in a summary, CSI2, which was designed for camera, it's camera serial interface, designed for cameras, but it's gaining popularity in, designed by MIPI, mobile industry, but getting a lot of traction in automotive industry for cameras as well as non-cameras. The major reasons being ability to carry high bandwidth, low pin count, ability to have multi-camera architectures without any design change, high quality, for both image quality and the quality of reliability and data, safety, ability to send pixel data, radar data, as well as ancillary data over the same link, so which can be used by the GPU or the application processor to increase the safety system, safety level of the system. And in future, there are a lot of changes coming on, but one big change is immediately which is coming is increasing number of virtual channels, which is right now limited to 4. So you can connect up to 4 devices per CSI interface, and we see we are already running out of the limit there. So in the next maybe 2.0 specification, we're going to support 32 virtual channels, so you can add a lot more devices. I see I'm running out of time, so I'm going to now leave the floor open to questions. Yes, please.
I think you're talking about CSI interface between your SerDes chip and the ADAS chip. Is that right?
That's correct.
Both are on the same board?
Both what?
Both the SerDes and your ADAS chip are on the same board?
So when you say SerDes is a serializer deserializer pair.
Yes.
So deserializer and the vision processor are going to be on the same board.
What I'm trying to understand is where is the CSI link? CSI link is not between the camera and ADAS chip, right?
So CSI link is in 2 places. So there is camera and serializer which are on the same board, connected by a long FPD link cable to deserializer and the vision processor which are on the same board. So there is a CSI link between the deserializer board and the processor, and there is another CSI link between the camera and the serializer.
But the actual physical links are still the cables.
I mean, you have, everything is physical. So
CSI is, I'm just trying to understand where is CSI coming into picture here. So CSI is between camera and serializer and your...
And between deserializer and the vision processor. Okay. So the deserializer part is very interesting because that's what, acts as the camera aggregator. That's what generates the virtual channel IDs. That's what takes the 4 cameras and connects them into a single stream. So instead of 4 cameras which require 48 pins, it does the job in 8 or 10 pins. So the deserializer to vision processor, that part is the one which is most interesting here. Okay. Yes, please.
Hi. Thanks for the presentation. It's very interesting. Actually, I wanted to ask the same as the previous question. What is the protocol between the serializer and the serializer? Is it proprietary or is it something like Ethernet?
No, it's not Ethernet. It's FPD-Link, which is not proprietary. And TI is not the only vendor which is supplying that. There is Maxim, and I think there are some other vendors also which are doing that. So FPD-Link is fairly common.
What's the name? I didn't get it.
FPD, it stands for flat panel display.
Oh.
It was designed originally for the laptop displays, but again, it's being repurposed for a lot of different applications.
I had another question about how you distribute the bandwidth between the different cameras. So do you have some protocol to negotiate the amount of bandwidth to allocate to each camera, or must they all share the same bandwidth?
So I can tell you in automotive, there should not be any need for any negotiation. We should have create enough bandwidth that even in worst case, all of them should get enough bandwidth. So there should not be packet dropping. I mean, system should not be designed for packet dropping. There should be ample bandwidth with enough overheads so that all the cameras or all the devices can get as much channel allocation as they want.
I understand, but if you have cameras that have lower megapixels and cameras that have higher megapixels, higher frame rate, you cannot allocate different bandwidths to them?
So you don't have to allocate the bandwidth, it's all shared. So, and that's the beauty of CSI too. It is just one link which is shared between all the cameras, and as long as the sum total of all the cameras is less than the bandwidth support of that link, you don't have to do any.
So it's a simple round robin arbitration? Okay.
Yeah. And I guess probably there, maybe we have to transition to the next speaker.
Yeah.
Yeah, I'm over the limit.
I think you'll be around in the outside area in case there are any other questions.
Sure, yes. Yeah, so I'm out of my time, so sorry for that. But if you have any questions, you can always find me here. Okay. Thank you very much.
Okay, well, thank you very much.